Welcome back. It's good to have you back for the third section of Chapter 3. We're going to talk about the second derivative test this time, and that has mostly to do with your graph being concave up or concave down. It's an easy check, and if you followed what went on in the previous section about the first derivative test, this will be right up your alley. But make sure that you got what you might call a cheat sheet, lots of notes, and get the formulas, get little tables, things that you can have in front of you. You're going to need them for the test, and you're going to need them to keep up with what we're going to do next. Now, the good news is that even though this might seem a little bit exotic, it really is a lead in to the next section, which is on optimization. Now, by optimization, what I'm talking about is if you've got a business, one of the things you want to optimize is the profit, right? Because you want to go on vacation during the winter time, perhaps. Or maybe you want to keep the cost down, so you want to minimize the cost. And that's what it's all about. And the second derivative test, as well as the first derivative test, help you to find out where you can actually make these decisions and how you can make them. So here are some things we're going to, first I want to make sure my notation, okay, we're good. Find the intervals on which it's concave upward or concave downward. And you'll be surprised at how easy this is. And the only thing you might need to be concerned about is getting the first derivative and the second derivative separate. They do different things. They work together hand in hand, but you want to make sure your notes are really good, okay? So I have a section for the first derivative things and the section for the second derivative things. Second of all, points of inflection, and as a quick note, that means when it goes from being curved like this to curved like that, or vice versa. The place where it switches from going up to going down is a place like this. On this side, it's curved downward. On this side, it's curved upward, open upward. And the place where it switches is called the point of inflection. Now, you're not too concerned about this, although there is one thing that's important about it. But the naming itself, the point of inflection, is not a big deal for you in business calculus. But you do need it for something that's coming up, and I'll hold that back. But we'll get there. So the second derivative test helps you find the relative extrema. What is that? That sounds a little bit extreme, right? All it means is a relative minimum or relative maximum. And what does that translate to? It translates to in a certain interval of your graph. Do you have a high point or do you have a low point? That's what it really amounts to. And if you're talking about cost or profit or revenue, that's important. And if you can find out where that's happening and at the production level that's happening or the sales level that's happening, you can make the most money. That's what it's all about. Points of diminishing returns. Guess what? Points of inflection are going to tell you that. We'll talk about that a little bit more in its own time. In the meantime, let's move on. So concavity. Concavity just means you've got a graph and either it opens upward or it opens downward. It's sort of like a cave, except that it's open upward or downward instead of it like this. So here you are walking into a cave, except that cave is either like this or like that. Next. So we've talked about finding the intervals over which the function itself increases or decreases. Now be careful. Make sure your notes are good. There are places where f increases or decreases, and then separately where the derivative increases or decreases is a different story. It's a different story. Sorry to repeat myself, but just make sure you keep those separate. So you want to keep two separate notes, sort of like this. And first derivative on this page, and second derivative on that page or on the same page with a split in the middle. Just an idea. You can do it any way you like. So we'll see about locating the intervals where f prime increases or decreases. Notice this is f, this is f prime, or the derivative. Different. Where this increases or decreases determines whether it's curving upward or curving downward. So put this on one section and this on another section. It might be a good idea if you maybe use a highlighter, whatever you need to contrast the two, because it's different. So this is very simple. We won't spend a lot of time on this. Of course, we're assuming f is differentiable, and usually we assume that anyway. It's not a big deal for us in business calculus. But here we go. Concave upward, like this, when f prime is increasing. Concave down, where f prime is decreasing on the interval. Now remember, this is the derivative is increasing or the derivative is decreasing. It's not whether the function is. So you have to be very careful about that. You don't want to get these two confused. So let's take a look at the picture. Concave upward looks like this. And it's concave upward if the graph appears above the tangent line. So there's a tangent line down here, and the graph is totally above it. So it's concave upward. Concave downward, the graph is below one of its tangent lines, or all its tangent lines, really. Now, the test for which kind of concave graph we have. This is very important, so make sure you've got this note with the second derivative information. When the second derivative is positive on some interval, remember it's on intervals we're talking about, then it's concave upward. So second derivative positive means you've got this. Second, as you might guess, if the second derivative is negative, then that section of the graph looks like this, roughly speaking. So how you use this? Okay, first, find the x values where you've got a second derivative 0 or undefined. Those are like your critical values were for the first derivative test. Only they're critical values in a different sense because you're talking about the second derivative instead. Use those values because what you're going to do, you're going to take these values on the number line, and those values will split the number line into several sections. those are your test intervals, or your intervals. All you need to do next is to check any point in each of those intervals and see whether it's positive or negative. So for this particular first one, see what the second derivative is in that section. You can use any point back here at all, any point at all. Put it into the second derivative. Is it positive or is it negative? If it's positive, then you've got concave upward. If it's negative, then it's concave downward. It's that easy, really. If you can keep all this stuff straight. Then you go on to this one. Take your same second derivative, use a test point in this interval, see whether it's positive, in which case it's concave upward, or is it negative in this interval. You can choose any point at all, just like you did before. Any point at all. And all you care about is it positive? Is it negative? If it's 0, then it's not telling you anything. Sorry about that. Just positive versus negative, concave upward or concave downward. So you find those values, make a list of your test intervals. We'll show you a table coming up, just very similar to the one we used for the first derivative. And with those test intervals, test the sign in each test interval with any x that you like within that test interval. So here's one to try with. I've got a function here. This is f. And of course, what you're going to need is not only f, you're going to need the first derivative, and you're going to need the second derivative. So, is it concave upward or is it concave downward, and on what intervals? So first, we'll find the second derivative. Well, a little bit of a rewrite first. Use a chain rule to finish this. And there's our first derivative. We need the second derivative. So, we'll invoke the quotient rule for that one. Simplify. Simplify a little bit more. And what we need to find is where that is 0 or where it's undefined. Well, as you notice, if you set that equal to 0, this part here, you set that equal to 0, you get a positive or negative 1. Now, if you look at the denominator, you've got a number that's squared, so that's positive. Add it to 3. This denominator is never going to be 0, so you don't have to worry about it being undefined. So we've got 3 test intervals, negative infinity to the first of those numbers, between those two, and from 1 to positive infinity. Now you're going to pick some points inside those intervals, anything at all, whatever you find convenient, because you're going to put it in here. You're going to pick an x, there's your x, and oops, that didn't look too well, that's your x. You're going to put it in here where the x's are, and all you care about is it positive? That means it's concave up. Or is it negative? It's concave down. That's it. Get those points. Ta-da! Split the number line up into test intervals. Find test points. For example, maybe your test points would be -3. 0 would be convenient there, and maybe a 5 there. Anything you like, really. And you'll put it in the second derivative to see whether it's positive or negative. So there is a good table for you. First of all, you find out what those points are, so you can split the number line into test intervals. Write down the test intervals on the first line. Mark off your table. Pick what your test values are going to be. -2 is in here somewhere. 0 is in here. And 2 is in there. What do you need to do with those? Just put them in the second derivative and see what happens compared to 0. Positive, negative, 0. And what do you get? Well, this one was positive, so it's concave upward on this interval. This one was negative, so it's concave downward in this interval. And in the third one, this turned out to be positive, so it's concave upward on that interval. And if you look down here, this gives you a picture of what's going on. Here were the 2 points we found by investigating the second derivative. Here are the intervals. Here's interval number 1, interval number 2, interval number 3. And you use these 3 test points and just check positive or negative of the second derivative there to see whether it's concave upward or downward in those intervals. Good table to keep in mind. In fact, better yet, make a copy of it. Make a copy of this one, along with maybe a note as to how you got these intervals. And then a blank one that has nothing in it except for what you're doing in that particular row. Points of inflection. Well, what are we talking about here? It's not exotic. That's where we go from concave upward to concave downward, or vice versa. So you're going to use your table like you had back here to decide whether you've got a point of inflection or not. So there's some pictures of points of inflection. Notice on, where am I? Right here. Okay, on this one. This is concave upward here, concave downward here. Where it switches between the two is your point of inflection. Here you have concave downward to concave upward, and it switches between the two at that point. So it's a point of inflection. On this one, concave upward, concave downward, there's the point where you're switching between the two orientations. And there you go. You can read that if you like. Add it to your notes. And add notes to the notes so it makes sense to you. Next. So to get those points of inflection, you might want a separate category for here. To get the points of inflection, you want to locate them. So set your second derivative equal to 0. See what you get for x's. Possible points of inflection. Also see if that denominator can be 0. That would give you an undefined second derivative. All of these are going to give you those possible points of inflection. It's sort of like critical points were for the first derivative. Except these are critical numbers. They're critical numbers for f, but in a different way. Those are where you're going to look for relative extrema. In other words, maxima and minima. Now this can be a little bit exotic when we get to these, but this says for one of those critical points. Now there's your x value. Put the x value into f, and you get the second coordinate, or the point of inflection. And it's a point of inflection if the second derivative is 0, or it's undefined. Those are possible points of inflection. Oops. So let's take a look at a real one. Here's a nice polynomial, so it's a nice one. Find its points of inflection. Let's see how this goes. First of all, we need the second derivative. So write the function. Find the first derivative. If you're lagging a little bit on this, make sure you do this. Don't just let it show up on the screen on you. Slip back here, do it yourself. Make sure it's the same thing that shows up right here. And take the second derivative, and there we go. We picked a polynomial because it's easy to work with. So we can focus on finding the points of inflection. So what's next? We're going to factor that. You don't have to, but it does make things a little bit easier. Another thing you could do, you could just divide all of this, because you're going to set it equal to 0. You can divide all of this by the common factor of 6, which makes it 2x squared plus x minus 1. Factor that, and this is what you're going to be working with. Set those equal to 0, and here are your two possible points of inflection, derived from the second derivative, set equal to 0. Now these 2 points are going to split the number line into 3 sections. Notice the -1 comes first, so you have negative infinity to -1, -1 to 1/2, and 1/2 to positive infinity. This splits the number line, just like this. 0's here. You got a section up to here. That's 1. You got from here to about here. That's the second section. And then over here, from there on the positive infinity. 3 sections that was split up using the second derivative. Here's what it actually looks like. So you can see what's happening. On the first one, it's concave upward. Second area, second interval, it's concave downward. And then the last one is concave upward. So the points of inflection are here and here. Now, finding this and this is what you've just done. To get the second coordinate, remember, all you have to do is put the first number, the x, into the function itself and find out what the y value is. So, the second derivative test. We can use it to find relative minima and maxima. Important for business, important for lots of applications. If you've got an equation or a formula you can work with, this helps you find those places. So it's a function that the first derivative is 0, and the graph is concave upward at x equals c. And that means you're going to have a relative minimum. Okay, what are we talking about? Well, if it's concave upward, then it has the smallest point here. And that's why it's called a minimum, because the y value is the smallest possible in that interval. So here's a picture. Here's one section, one interval where it's concave downward, and because concave downward, it has a maximum, or relative maximum that is, because we don't know what's happening over here. And this one's concave upward. That means we've got a relative minimum. Now we don't know what's happening over here or over here. That's why it's a relative maximum or a minimum. All we care about is the interval, in this case from here to here. So here's something you also want to add to your notes, if the first derivative is 0, let the second derivative exist on the open interval containing c. Then if the second derivative is 0, you have a relative minimum at x equals c. If that second derivative is negative, that means it's open upward, it's a relative maximum. And the bad news is if your second derivative at that critical point is 0, the test fails. So you won't have a relative maximum or a minimum, either one. Okay, let's see what we can do with this one. Notice it's a nice polynomial, so it won't be too hard to work with. So we'll find the first derivative. You could factor first if you want to. You can see that here's the derivative. You've got the first derivative. Factor that. This part gives you x equals 0 when you set that equals 0. This one gives you the -1 and the +1. Those are the only critical numbers of f. 0, -1, and +1. Those are the critical numbers. Okay, we've got a small table for us. We've got a point, -1, -2, 0, 0, and 1, 2. What's the sign? On -1, it's positive. 0, it's 0. That means the test fails here. And negative here. So here, since it's positive, that means we're going to have a minimum in that interval. Over here, it's negative, so we'll have a maximum. Add those to your growing list of notes. You're going to be able to use these notes on any test, so it's very, very important. So the test for concavity would show that, notice this was a relative minimum, okay, you can see that. Over here, relative maximum, yes. This one is not, because this is increasing here and continues to increase here. It doesn't go from increasing to decreasing or vice versa. So this is not a relative maximum or minimum. And to wrap it up, now we were talking about points of inflection. This is what we're getting to. Diminishing returns at points of inflection. Ta-da! Okay. So we've got a function here. The input's in dollars, and the output is in dollars. For example, this might be for, maybe these are advertising dollars, and these are sales dollars. So it looks as though the X represents the input in dollars, so maybe this is advertising, for example, say on the internet. The more you advertise, the more your sales increase to a certain point, and then when you spend more, you don't get as much out of it as you did before. Sales are increasing, but not like they were before. So that would be the point of diminishing returns. Each additional dollar returns more than the previous dollar in the first interval, where it's going like this. However, on the second interval, you're getting more dollars, but not as quickly as you did before. Each additional dollar doesn't bring back as much as it did previously. That's the point of diminishing returns. And this is something you'll learn in economics. It's a little bit past my pay grade. But the increased investment beyond that point, the point of diminishing returns or the point of inflection, usually more investment past that is a poor use of your money going into the business. Here's an example, and this is where I got the idea really. Increasing its advertising cost. Company discovers it can increase the sales, so this is sales on this side, according to this model. And this, the X is the advertising cost. Find the point of diminishing returns. Well, for us at this point, that means can we find a point of inflection where it goes from increasing to increasing, but not as well as it did before. So first of all, we'll find the first derivative, then we'll find the second derivative, and we'll set it equal to 0. Well, it only is 0 where x equals 20. You can actually do the work yourself. Don't believe everything you see on the screen. Try it yourself, because you're going to have to do it by yourself in the exercises. And this is a picture of what it looks like. So here we are. Our sales are like this, and we decide we're going to advertise, because I think we can make some more money if we advertise. So we start advertising, and our sales get better and better and better and better up to a certain point. After that, the sales are going up, but they're not increasing the way they did before. So you wouldn't want to go beyond that if you can help it. Well, that's it, folks. That is section 3, and that's how we can use the first derivative and the second derivative to help us find some answers. Well, you take care of yourself and keep smiling. See you next time.